Look up at the night sky, and what do you see? A scattering of stars, maybe the faint glow of a distant galaxy. But what if I told you the universe holds structures so vast they make entire galaxies look like specks of dust? Imagine something 1 billion light-years across, a cosmic web so immense it bends the rules of physics as we know it. These aren't just clusters of stars or clouds of gas. These are the largest constructions in existence, woven into the fabric of space itself, and they're hiding secrets that could rewrite our understanding of reality. Think about the scale for a moment. Our Milky Way is already unimaginably huge, a swirling disk of hundreds of billions of stars, stretching 100,000 light-years from end to end. But out there, beyond the familiar glitter of our galactic neighborhood, lie titanic formations that dwarf even the grandest galaxies. Walls of galaxies spanning hundreds of millions of light-years, bubbles of energy left over from the birth of the universe, and voids so empty they could swallow thousands of Milky Ways without a trace. These aren't just random arrangements, they're the bones of the cosmos, the scaffolding upon which everything is built, and that's just the beginning. Over the next 30 mind-blowing facts, we're going to journey through the most colossal structures ever discovered, from the mysterious Great Attractor pulling entire galaxy clusters toward it, to the incomprehensibly vast Hercules-Corona Borealis Great Wall, stretching 10 billion light-years across the observable universe. We'll uncover how these giants shape the cosmos, what they tell us about the forces governing existence, and why some of them shouldn't even be possible according to our current science. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe isn't just a random scattering of galaxies, it's organized into an intricate, sprawling network like threads in a colossal spiderweb. Scientists call this the cosmic web, and it's the largest structure we've ever observed, stretching across billions of light-years. Picture this: galaxies aren't isolated islands in space but connected nodes, strung along vast filaments of dark matter and gas, with enormous voids, empty regions spanning hundreds of millions of light-years separating them. This web is the backbone of the cosmos, shaping how galaxies form, move, and even collide over cosmic time. But how did we discover something so unimaginably huge? It started with mapping the positions of galaxies using redshift surveys, a way to measure how fast distant galaxies are moving away from us due to the expansion of the universe. As astronomers charted more and more galaxies, they noticed something astonishing. Instead of being randomly spread out, galaxies clustered along faint, thread-like structures with gigantic gaps between them. The deeper they looked, the clearer the pattern became, a web of matter woven across the universe. And here's where dark matter comes in. This mysterious, invisible substance doesn't emit light, but its gravity acts like the framework of the cosmic web, pulling galaxies into these filamentary structures. In fact, without dark matter's gravitational scaffolding, galaxies would never have formed in such intricate patterns. It's as if the universe itself is a grand construction project, with dark matter as the blueprint and galaxies as the bricks, assembling themselves into this breathtaking cosmic architecture. What's truly mind-bending is the scale. Some of these filaments stretch for hundreds of millions, even billions of light-years, forming boundaries around voids so empty they defy comprehension. Imagine flying through one of these voids. You could travel for lifetimes and never encounter a single star. Yet even in these desolate stretches, the universe whispers its secrets, revealing how matter and emptiness balance each other in an endless dance. The cosmic web isn't just a structure, it's the story of how everything in existence came to be. Stretching an almost incomprehensible 10 billion light-years across the observable universe, the Hercules-Corona Borealis Great Wall isn't just large, it redefines what we thought was possible. Discovered in 2013 by mapping gamma-ray bursts, this colossal filament of galaxies shattered expectations, forcing astronomers to question one of cosmology's fundamental rules, the cosmological principle. This principle states that, on large enough scales, the universe should look roughly the same no matter where you are, but the Hercules-Corona Borealis Great Wall. It's so enormous that it throws that assumption into doubt. To grasp just how big this structure is, picture our entire Milky Way galaxy, 100,000 light-years wide, as a single grain of sand. Now imagine a structure so vast it would take 100,000 Milky Ways lined up end to end just to cross it. That's the scale we're dealing with. And it wasn't found by peering through telescopes at visible light. Instead, scientists pieced it together by tracking gamma-ray bursts, the brightest explosions in the universe caused by collapsing massive stars or colliding neutron stars. These bursts act like cosmic breadcrumbs, revealing the hidden distribution of galaxies across unimaginable distances. What makes this discovery so controversial? According to our best models, structures shouldn't grow this large. The universe is only 13.8 billion years old, not nearly enough time for gravity to pull matter into formations spanning nearly 3/4 of the observable cosmos. It's like stirring a cup of coffee and finding, instead of an even swirl, that all the creamer has clustered into a single continent-sized pattern. Some theories suggest dark energy or anomalies in the early universe might explain it, but for now, the Hercules-Corona Borealis Great Wall remains one of astronomy's most tantalizing mysteries. And here's the kicker: we might not even be seeing the full picture. Because gamma-ray bursts can only reveal so much, parts of this cosmic leviathan could extend even farther, lurking just beyond our current observational limits. If confirmed, that could mean we're staring at the edge of something even more monumental, a structure so vast it bends not just the rules of physics, but our very understanding of the universe itself. One thing's certain: the cosmos still has surprises up its sleeve, and this wall is proof that when it comes to size, the universe plays by its own rules. Before the Hercules-Corona Borealis Great Wall rewrote the cosmic record books, another titan held the title, the Sloan Great Wall, a staggering thread of galaxies spanning 1.4 billion light-years. Discovered in 2003 by the Sloan Digital Sky Survey, this monumental structure didn't just break records, it shattered the way scientists thought about the universe's architecture. Imagine a river of galaxies so vast it would take light, the fastest thing in existence, 1.5 billion years just to travel from one end to the other. And yet, this isn't some distant, abstract formation. It's woven into the cosmic web relatively close to us, a mere 1 billion light-years away. The Sloan Great Wall wasn't found by accident. Astronomers meticulously mapped the positions of tens of thousands of galaxies, using redshift measurements to piece together their three-dimensional distribution. What emerged wasn't just a random scatter. It was a filamentary superstructure, a spine of galaxies stretching across the sky, bound together by gravity. This discovery was a game-changer because it revealed that the universe's large-scale structure wasn't just clumpy. It was organized into interconnected walls and filaments on scales far grander than anyone had anticipated. Here's what makes it so fascinating. The Sloan Great Wall defied theoretical predictions about how large cosmic structures could grow. According to models based on the standard Big Bang theory, matter shouldn't have had enough time to clump together into something this enormous. It's like shaking a box of marbles and finding, instead of a mostly even spread, that half of them had mysteriously arranged themselves into a single, perfectly straight line. Some scientists suggested that dark energy, the mysterious force accelerating the universe's expansion, might have played a role in shaping these walls by subtly influencing how matter clustered in the early cosmos. But the real kicker, the Sloan Great Wall, is just one of many. As our telescopes peer deeper into space, we're finding that these gargantuan walls might be more common than we ever imagined, hinting at something profound about the universe's underlying structure. And while newer discoveries have dethroned it as the largest known structure, its legacy endures, proving that the cosmos isn't just vast, but intricately, almost artistically, organized on scales that humble even the boldest imaginations. What's next? As technology advances, we might uncover even larger formations, pushing the boundaries of what we thought possible. The Sloan Great Wall was just the beginning, a cosmic wake-up call reminding us that the universe loves to outdo itself. And if history is any guide, the next record breaker is already out there, waiting to be found. Buried behind the luminous haze of our own Milky Way lies one of the most elusive cosmic giants ever detected: the South Pole Wall, a curtain of galaxies stretching 1.4 billion light-years across the southern celestial hemisphere. Discovered in 2020, this colossal structure remained hidden for decades, obscured by the dense star fields and interstellar dust of our galaxy's disk. But how do you map something you can't even see? The answer lies in a brilliant workaround. Instead of relying on visible light, astronomers turned to the subtle tug of gravity itself. By studying the peculiar motions of galaxies, tracking how their paths deviate from the universe's overall expansion, scientists reconstructed the invisible scaffolding of dark matter that must be pulling them. Think of it like listening to the whispers of leaves rustling in the wind to map the shape of an unseen valley. These gravitational clues revealed a vast sheet of galaxies, aligned like pearls on a string, arcing behind the Milky Way's blinding glare. What's astonishing isn't just its size, but its proximity. The South Pole Wall lies a mere 500 million light-years away, making it one of the closest megastructures to our cosmic neighborhood. But the real breakthrough was the technique used to uncover it. Traditional galaxy surveys hit a wall literally when facing the Milky Way's zone of avoidance, a swath of sky where our galaxy's dust and stars block the view beyond. To peer through this cosmic blind spot, researchers combined two cutting-edge methods: redshift surveys to measure galaxy movements and gravitational simulations to fill in the gaps where observations failed. It's like completing a puzzle with half the pieces missing by using the shadows they cast to guess their shapes. What makes the South Pole Wall so intriguing isn't just its scale, it's the way it challenges our understanding of cosmic evolution. Structures this massive shouldn't form so close to us, according to some models. Its sheer density suggests that dark matter and dark energy might be orchestrating the universe's large-scale structure in ways we're only beginning to grasp. And with more hidden giants likely lurking behind the Milky Way's veil, this discovery hints at an even grander cosmic blueprint, one we're just scratching the surface of. The hunt for these obscured titans is far from over. New telescopes like the upcoming Vera Rubin Observatory promise to peel back the Milky Way's curtain further, potentially revealing even larger structures hiding in plain sight. The South Pole Wall isn't just a scientific curiosity, it's a reminder that the universe still holds secrets in its shadows, waiting for the right tools and the right minds to bring them into the light. The Milky Way isn't floating through space alone. It's part of something far grander, a galactic metropolis known as the Laniakea supercluster. Encompassing 520 million light-years and 100,000 galaxies, this sprawling cosmic neighborhood redefines what it means to feel at home in the universe. The name Laniakea comes from the Hawaiian words for immense heaven, and it couldn't be more fitting. Picture a colossal river system, but instead of water, currents of galaxies flow along invisible gravitational pathways, all moving toward a mysterious focal point deep in space. What makes Laniakea truly remarkable isn't just its size, it's how galaxies move within it. Using advanced mapping techniques, astronomers discovered that every galaxy in this supercluster, including our own, is being drawn toward a gravitational hotspot called the Great Attractor, hidden behind the Milky Way's dusty plain. It's as if the entire supercluster is caught in a slow-motion cascade, with galaxies sliding along cosmic tributaries toward some unseen drain, our Milky Way. We're on the outskirts, like a suburban resident commuting toward a distant downtown. But here's where it gets even wilder. Laniakea isn't a static structure. It's constantly evolving, its boundaries shifting as astronomers refine their understanding of galactic motion. Unlike traditional superclusters defined by visible galaxy groupings, Laniakea was mapped by tracing the subtle flows of galaxies through space, revealing an interconnected web of motion invisible to traditional telescopes. Imagine trying to map a city by watching commuter traffic instead of looking at buildings. That's how scientists pieced together this cosmic megalopolis. Yet for all its grandeur, Laniakea might just be one thread in an even larger tapestry. Some studies suggest it could be part of an inconceivably vast structure called the Pisces-Cetus supercluster complex, hinting at scales that stretch our comprehension to the breaking point. And while 520 million light-years sounds impossibly huge, remember this. In the cosmic web, even Laniakea is just a neighborhood, one district in a universe that never stops reminding us how small we truly are. The discovery of Laniakea didn't just give us a new cosmic address, it changed how we see our place in the universe. No longer isolated wanderers, we're part of an immense celestial watershed, riding gravity's currents toward destinations we're only beginning to understand. And as telescopes grow more powerful, who knows what other supercluster secrets might be waiting just beyond the edge of our current maps? One thing's certain, the universe loves scale, and Laniakea is proof that home is far bigger than we ever dreamed. 650 million light-years from Earth lies a gravitational heavyweight, the Shapley supercluster, a dense swarm of galaxies so massive it warps the very fabric of space around it. Picture a cosmic magnet pulling everything in its vicinity toward its core with irresistible force. This isn't just another cluster, it's a sprawling metropolis of galaxies, home to at least 20 massive galaxy clusters and thousands of individual galaxies packed into a region roughly 400 times the volume of our local group. If our Milky Way were a single house, the Shapley supercluster would be an entire continent, crowded, luminous, and dominating its corner of the universe. What makes Shapley extraordinary isn't just its size, but its gravitational reach. Astronomers discovered something peculiar about the motion of our local group, the collection of galaxies that includes the Milky Way. Even after accounting for the expansion of the universe, our galactic neighborhood is moving at over 600 kilometers per second toward a mysterious point in space. For decades, scientists suspected the Great Attractor was responsible, but further research revealed an even bigger player, the Shapley supercluster, acting like a hidden anchor in the cosmic tug-of-war. Its immense mass, estimated to be 10,000 times that of the Milky Way, creates a gravitational well so deep it's pulling entire superclusters, including ours, toward it. Mapping Shapley's influence was like solving a celestial whodunit. By studying the subtle distortions in galaxy motions across vast distances, astronomers pieced together its role in shaping the flow of the local universe. Think of it as tracking the source of a river's current by watching how leaves drift downstream, except here, the leaves are galaxies and the current is the relentless pull of dark matter and gravity. The Shapley supercluster doesn't just sit there, it actively molds the cosmic landscape around it, bending the paths of galaxies and even light itself as they pass by. Yet for all its power, Shapley remains shrouded in mystery. Its core is so densely packed with galaxies that their combined light creates a fog of radiation, making it difficult to study individual members. Some theorists speculate that superclusters like Shapley might be the universe's way of balancing the scales, counteracting the vast, empty voids that dominate cosmic geography. Others wonder if these colossal structures are temporary, destined to dissolve as dark energy accelerates the universe's expansion. One thing's certain, as long as Shapley's gravity keeps pulling, it will remain a cornerstone of our understanding of how the universe organizes itself and how even the mightiest structures whisper to us across the abyss. If the Laniakea supercluster felt immense, brace yourself. It's just one neighborhood in an even grander cosmic city, the Pisces-Cetus supercluster complex, a sprawling network of galaxy filaments spanning a staggering 1 billion light-years. Imagine the universe as a vast ocean, and these superclusters as continents adrift in the darkness, connected by hidden underwater mountain ranges. That's essentially what Pisces-Cetus is, a bridge of galaxies linking titanic structures like Laniakea and others into a web of unfathomable scale. What makes this complex so fascinating isn't just its size, but how it forms. These galaxy filaments aren't random. They trace the edges of cosmic voids, enormous bubbles of near-empty space that stretch hundreds of millions of light-years across. Picture blowing soap bubbles. The delicate films where bubbles meet form intricate walls and channels, just like galaxies clustering along the boundaries of these voids. Gravity does the rest, pulling matter into dense strands over billions of years, leaving the voids emptier and the filaments richer with stars. Here's where it gets even more mind-bending. The Pisces-Cetus complex isn't just a static structure, it's a snapshot of an eternal cosmic dance. As the universe expands, these filaments stretch and evolve, with galaxies flowing along them like cars on a freeway. Some collide, merging into colossal clusters, while others drift apart, carried by the currents of dark energy. And just like city lights visible from space, the galaxies in these filaments trace the outline of something far larger, the cosmic web itself, with Pisces-Cetus as one of its most magnificent threads. But why study something so impossibly vast? Because these supercluster complexes hold clues to the universe's fate. Their growth or eventual dissolution could reveal whether dark energy will one day tear the cosmic web apart. For now, Pisces-Cetus stands as a testament to the universe's love of patterns, proving that even in the grandest scales, there's an order to the chaos, a blueprint written in gravity, dark matter, and time. Hidden behind the Milky Way's dazzling disk lies one of the universe's greatest cosmic puzzles, the Great Attractor, a gravitational behemoth dragging entire galaxies toward it at over 600 kilometers per second. For decades, this invisible force baffled astronomers, its secrets locked away in what they call the zone of avoidance, a region of sky where our galaxy's thick dust and stars block nearly a fifth of our view into deep space. Imagine trying to study a roaring waterfall while standing downstream in a thick fog. That's the challenge scientists faced as they grappled with this mysterious pull reshaping our cosmic neighborhood. The breakthrough came when astronomers realized they didn't need to see the Great Attractor directly. They could map its influence by watching how galaxies move around it. Like detectives tracking a criminal's whereabouts by following the crowd's startled glances, they studied peculiar galaxy motions, spotting a cosmic river of star systems all flowing toward the same unseen destination. X-ray observations eventually pierced the veil, revealing a dense cluster of galaxies near the Norma constellation, packed with enough mass to explain some but not all of the gravitational pull. This turned the Great Attractor from a single mystery into a layered cosmic riddle. What makes this phenomenon so fascinating isn't just its hidden nature, it's the scale of its impact. The local group containing our Milky Way and Andromeda galaxies isn't just drifting aimlessly through space. We're caught in this grand celestial current, along with thousands of other galaxies across the Laniakea supercluster. Yet here's the twist: the Great Attractor itself appears to be moving, pulled toward something even larger, the monstrous Shapley supercluster, nearly 700 million light-years away. This creates a cosmic chain of gravitational dominance, where each structure tugs on the next in an endless hierarchy of influence. Modern radio telescopes like Laniakea are finally peeling back the Milky Way's obscuring curtain, revealing more galaxies hiding in the zone of avoidance. Each new discovery adds pieces to this gravitational jigsaw puzzle, showing that what we once thought was a single attractor might actually be multiple dense regions working together. The story of the Great Attractor isn't over. It's evolving right along with our ability to peer deeper into the universe's hidden architecture. And as technology improves, we may find that this cosmic mystery was just the first clue in uncovering far grander structures still lurking in the shadows of our own galaxy's glow. In the vast cosmic quilt of galaxy clusters and voids, astronomers recently stumbled upon a pattern so colossal it defies explanation. The giant arc, a crescent of galaxies spanning an astonishing 3.3 billion light-years. To put that into perspective, if you traveled at the speed of light, it would take you longer to cross this structure than the Earth has existed as a planet. Discovered in 2021 by analyzing the light from distant quasars, this formation isn't just big, it challenges one of cosmology's bedrock ideas, the cosmological principle, which states that on large enough scales, the universe should appear roughly uniform no matter where you look. The giant arc shatters that assumption like a hammer through glass. What makes this discovery so groundbreaking isn't just its size, it's the improbability of its existence. Current simulations of the universe's evolution suggest that structures shouldn't naturally grow beyond 1.2 billion light-years. Yet here we have something nearly 3 times that scale, a chain of galaxies and gas clouds so vast it resembles a smile stretching across a third of the observable universe. Imagine stirring cream into coffee, and instead of blending smoothly, you find it's formed perfect concentric circles. That's the level of cosmic eyebrow raise we're dealing with. The giant arc shouldn't be there, but it is. The detection method itself was ingenious. Astronomers didn't see the arc directly. They mapped it by observing how its gravitational pull subtly distorted the light from even more distant quasars, those brilliant cores of ancient galaxies. It's like finding the outline of a mountain range at night by watching how it blocks stars on the horizon. This technique revealed dozens of galaxy clusters and intergalactic gas clouds aligned in a curve so precise it can't be coincidence. What's wild is that the arc isn't some distant anomaly. It's relatively nearby in cosmic terms, just 9 billion light-years away, meaning we're seeing it as it existed when the universe was barely half its current age. Now, the real puzzle: if the cosmological principle holds that matter should be evenly distributed at grand scales, how did such a gigantic, lopsided structure form? Some theorists suggest early universe conditions might have sown seeds for these megastructures through exotic physics we haven't yet grasped. Perhaps quirks in dark matter behavior or ripples from cosmic inflation. Others whisper an even more radical idea. What if the universe isn't as uniform as we thought? What if, like an unevenly baked cake, it has regions of unexpected density that our current models fail to predict? For now, the giant arc stands as both a revelation and a provocation, a celestial monument demanding we rethink our place in the cosmos. As telescopes like the James Webb peer deeper into space, who knows what other impossible structures might emerge from the darkness? One thing's certain: the universe loves to surprise us, and every time we think we've grasped its rules, it paints outside the lines in ways that leave us humbled and astonished. Deep in the northern constellation of Boötes lies one of the universe's most unsettling mysteries, a yawning sphere of nothingness so vast it could swallow thousands of galaxies whole. Known as the Boötes Void, this incomprehensible emptiness stretches 330 million light-years across, yet contains fewer than 60 galaxies where scientists would expect tens of thousands. Picture throwing a handful of sand into an Olympic-sized swimming pool. That's roughly the density of matter in this cosmic desert. First discovered in the 1980s during galaxy redshift surveys, the void wasn't just an anomaly. It was a staggering contradiction to everything we thought we knew about how matter organizes itself across the cosmos. So how does something this empty even form? The leading theory points to an ancient game of gravitational tug-of-war. In the early universe, slight density fluctuations caused matter to clump unevenly. Over billions of years, galaxies attracted more galaxies, growing into dense clusters and filaments while the regions between them were gradually stripped bare. The Boötes void might be the ultimate loser in this cosmic land grab, its matter siphoned away by surrounding superclusters until only a ghostly shell remained. But here's where things get weird. Some simulations suggest the void is too big and too spherical to form naturally through this process alone. Its perfect emptiness feels almost engineered. That unsettling perfection has spawned wilder explanations. Could it be evidence of advanced civilizations somehow harvesting galaxies on an unimaginable scale? Or perhaps the imprint of an exotic physics event in the early universe, a collision between space-time bubbles during cosmic inflation, leaving behind a scar of nothingness? The truth is likely less dramatic but no less profound. What makes the Boötes void so scientifically valuable isn't the fantastical theories it inspires. It's what the void reveals about the universe's underlying architecture. By studying its boundaries, astronomers have found galaxies with unusual properties, older, redder, and quieter than their counterparts in denser regions. It's as if they've been frozen in time, cut off from the dynamic interactions that drive galactic evolution elsewhere. These cosmic hermits offer a rare glimpse into how environment shapes galaxies over billions of years. Even more intriguing, the void appears to be growing, its edges slowly eroding as filaments of the cosmic web siphon away its remaining galaxies. Yet for all its emptiness, the Boötes void isn't completely barren. In 2015, astronomers discovered a lone spiral galaxy drifting near its center, a celestial castaway named MCG plus 1235 plus 36. How it survived the void's great evacuation is anyone's guess, but its very existence hints that even the universe's most desolate places might harbor secrets waiting for the right moment and the right telescope to reveal them. The Boötes void forces us to confront an uncomfortable truth. The universe isn't just a story of glittering galaxies and majestic clusters. Emptiness has its own role to play, shaping the cosmos as profoundly as any supercluster. And as we peer deeper into these voids, we might just find that what's missing teaches us far more than what's there. Hidden in the afterglow of the Big Bang itself lies one of cosmology's most perplexing anomalies, the cold spot, a chilling void in the cosmic microwave background radiation stretching over 1.8 billion light-years across. When scientists first mapped the CMB, the faint glow left over from the universe's infancy, they expected a nearly uniform temperature distribution, like the surface of a gently warming pond. Instead, they found this, a frigid patch in the constellation Eridanus, colder than its surroundings by about 70 microkelvins, as if someone had pressed an icy finger against the fabric of space-time. So what could possibly leave a fingerprint this large on the universe's oldest light? One leading theory points to an unimaginably vast cosmic void, a region with significantly fewer galaxies than average. As light travels through such a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolf effect. Think of it like rolling a marble up a hill. The steeper the hill, the more speed the marble loses. But here's the catch, even the largest known voids can't fully explain the cold spot's extreme temperature drop. The structure required would need to be so empty, so absurdly devoid of matter, that it strains our understanding of cosmic structure formation. This discrepancy has fueled wilder speculation. Some theorists propose the cold spot might be evidence of a collision with another universe during cosmic inflation, a multiverse bruise left by a sibling cosmos bumping against our own in the earliest moments of creation. It's a radical idea, suggesting that what we're seeing could be the first observable evidence of parallel universes. Others suggest exotic physics at play, perhaps a defect in spacetime itself, like a cosmic knot formed during the universe's rapid expansion, or dark energy behaving in ways we haven't yet imagined. Yet the mystery deepens when we look closer. recent galaxy surveys reveal that while the cold spot region does contain a significant void, dubbed the Eridanus supervoid, its size and emptiness don't fully account for the temperature anomaly. This leaves astronomers with two possibilities. Either we're missing something fundamental about how voids interact with CMB radiation, or the cold spot represents something far stranger than empty space. The James Webb Space Telescope may hold the key, peering deeper into this enigmatic region to map its galaxy distribution with unprecedented precision. What makes the cold spot so compelling isn't just its scientific implications, it's what it represents about our exploration of the cosmos. Like a detective finding a single unexplained fingerprint at a crime scene, cosmologists are left with a clue that could point to groundbreaking discoveries or merely highlight gaps in our current theories. Whether it's a window into the multiverse or simply a cosmic oddity we've yet to properly explain, the cold spot serves as a humbling reminder that even our most sophisticated models of the universe still have room for the extraordinary. And as we continue to probe its secrets, we might just find that the answers rewrite our understanding of reality itself. Stretching an almost inconceivable 4 billion light-years across the cosmos, the huge large quasar group isn't just a collection of brilliant galactic cores. It's a celestial formation so vast that its very existence makes astronomers question the foundational rules of the universe. Discovered in 2013, this sprawling assembly of 73 quasars, the blazing centers of ancient galaxies powered by supermassive black holes, forms a structure so immense that light would need half the age of our solar system just to travel from one end to the other. If you placed it over our local cosmic neighborhood, it would engulf everything from the Milky Way to the farthest reaches of the observable universe we can study today. What makes the huge LQG truly staggering isn't just its size. It's the way it defies one of cosmology's most cherished principles, the cosmological principle, which states that on sufficiently large scales, the universe should appear roughly uniform in all directions. According to this idea, matter should be distributed evenly when you zoom out far enough, like stirring cream into coffee until it blends smoothly. But the huge LQG shatters that expectation. Instead of blending into the cosmic background, these quasars cluster together in a filamentary structure that resembles a gargantuan, glowing spiderweb, one that theoretically shouldn't exist at such staggering dimensions. Here's why this is so controversial. Based on our best models of cosmic evolution, structures larger than 1.2 billion light-years shouldn't form because there simply hasn't been enough time since the Big Bang for gravity to pull matter into such enormous configurations. The huge LQG doesn't just nudge past that limit, it obliterates it, stretching more than 3 times beyond what theorists thought possible. Some researchers argue this could mean our understanding of the early universe is missing a crucial ingredient. Perhaps dark energy behaved differently in the past, or exotic physics during cosmic inflation planted seeds for these unimaginable structures. Others suggest the huge LQG might not be a single coherent structure at all, but a chance alignment of smaller groups seen from our vantage point, like mistaking scattered streetlights for a distant city when viewed from just the right angle. Yet the plot thickens when you examine how quasars form. These incredibly luminous objects are thought to mark regions where matter was densest in the early universe, meaning their clustering could trace the underlying skeleton of the cosmic web on scales we've never mapped before. If the huge LQG is real, not just a statistical fluke, it implies that the universe's largest structures might be even more intricate and interconnected than we ever imagined. The debate continues to rage in astronomy circles. Some teams have proposed even larger structures since the huge LQG's discovery, while others maintain that such formations must be observational illusions. What's undeniable is that discoveries like this force us to rethink our assumptions about the cosmos. Whether the huge LQG stands as a genuine challenge to cosmological orthodoxy or gets explained away by better data, it serves as a vital reminder. The universe has a habit of surprising us, and the closer we look, the more we realize how much we still have to learn about the grand tapestry of existence. The cold spot in the cosmic microwave background isn't just a scientific curiosity. It's a cosmic detective story with clues pointing in wildly different directions. One of the most compelling explanations involves something called the Eridanus supervoid, a vast region of space with significantly fewer galaxies than average. When photons from the CMB pass through such a void, they lose energy climbing out of its weakened gravitational field, an effect that should in theory leave a cold imprint on the microwave background. But here's the problem. Measurements show the Eridanus supervoid, while substantial, isn't nearly empty enough to account for the cold spot's dramatic temperature drop. It's like finding a puddle but being told the only possible explanation is an entire lake. The numbers just don't add up. This discrepancy has led some researchers to propose far more exotic origins. One tantalizing possibility is that the cold spot marks the collision point between our universe and a parallel bubble universe during cosmic inflation. In this scenario, the spot would be a cosmic bruise, a remnant of energy drained away as our universe brushed against another. Think of it like two soap bubbles bumping in a sink. Where they touch, there's a subtle dimple in their surfaces. If true, this would be the first observational hint of a multiverse, a concept previously relegated to theoretical speculation, but not everyone's convinced. Skeptics argue that the cold spot might simply be a statistical fluke, an unlikely but not impossible random variation in the CMB. After all, when you're mapping something as vast as the entire observable universe, anomalies are bound to appear somewhere. To test this, scientists have run countless simulations of the CMB, and while cold patches do emerge occasionally, none as extreme or as large as the one we observe. The odds of it being pure chance, less than 1 in 50. What makes the cold spot so fascinating isn't just the mystery itself, it's what its resolution could reveal about the fundamental nature of reality. If it's evidence of a multiverse, it would revolutionize our understanding of cosmology. If it's an unknown void phenomenon, it means our models of large-scale structure formation are missing something critical. And if it's just a fluke, well, even that would teach us something profound about the limits of our observations. New telescopes like the Simons Observatory and upcoming CMBS-4 project aim to study the cold spot with unprecedented precision. By measuring its polarization and fine-scale temperature variations, they might finally crack this cosmic cold case. Until then, the cold spot remains a beautiful enigma, a reminder that even in the era of precision cosmology, the universe still holds cards close to its chest. The Sloan Great Wall isn't just a random assortment of galaxies, it's a masterclass in cosmic architecture, where gravity has sculpted matter into an intricate web of dense clusters and wispy filaments. Zoom in on this colossal structure and you'll discover something remarkable. Galaxies don't just dot the expanse like scattered stars, they gather in tightly packed knots, connected by luminous threads of gas and dark matter. These knots, known as galaxy clusters, can contain thousands of galaxies bound together in a gravitational dance, while the filaments between them act like cosmic highways, channeling galaxies toward denser regions over billions of years. What makes this structure so mesmerizing is how it mirrors the universe's underlying blueprint. The densest clusters along the Sloan Great Wall, like the Coma cluster, are cosmic metropolises where galaxies collide and merge in spectacular displays. Meanwhile, the filaments resemble the delicate strands of a spiderweb, faint but pervasive, tracing the invisible scaffolding of dark matter that dictates where galaxies form. It's as if the universe took its largest paintbrush and swept these filaments across the void, leaving behind strokes of starry brilliance. But here's the twist: these filaments aren't just passive bridges, they're dynamic rivers of matter. Gas flows along them, feeding the clusters at their intersections like tributaries filling a lake. Some of this gas cools and condenses, sparking bursts of new star formation, while other regions remain quiet, their galaxies aging in isolation. The Sloan Great Wall becomes more than a structure, it's a living network, where the ebb and flow of materials shapes the fate of everything within it. Yet for all its grandeur, the wall isn't uniform. Some sections bristle with activity, while others appear eerily sparse. These variations hint at the complex history of the universe, where slight differences in initial density snowballed into the vast disparities we see today. It's a reminder that even the mightiest structures are born from subtle beginnings, tiny fluctuations in the early cosmos that grew, over billions of years, into the breathtaking cosmic web we now observe. The Sloan Great Wall doesn't just challenge our sense of scale. It reveals the delicate balance between chaos and order in the universe. Every cluster, every filament tells a story of gravity's patient work, weaving galaxies into patterns that stretch across the ages. And as we map more of these structures, we edge closer to answering one of cosmology's biggest questions. How did something so vast, so intricate, emerge from the primordial darkness? The wall holds clues written in the language of light and shadow, waiting for us to decipher them. Mapping the universe's largest structures requires more than powerful telescopes. It demands a revolution in how we collect data. Enter the Great Wall, a filament of galaxies stretching 1 billion light-years across the cosmos, uncovered by the Baryon Oscillations Spectroscopic Survey. This isn't just another supercluster, it's a testament to how cutting-edge redshift surveys are peeling back layers of the universe we never knew existed. Unlike traditional observations that relied on visible light, BOSS used a clever trick. By measuring subtle distortions in the light from over 1 million galaxies, it traced the invisible scaffolding of dark matter that shapes everything. What makes the Great Wall extraordinary isn't just its size, it's how it was found. Earlier surveys like Sloan mapped galaxies in relative proximity, but BOSS peered deeper, capturing light from quasars up to 12 billion light-years away. These ultra-bright beacons act like cosmic lighthouses. As their light passes through clouds of intergalactic hydrogen, it leaves absorption lines in their spectra, a fingerprint revealing the universe's hidden structure. Imagine using shadows to reconstruct the shape of an unseen mountain range. That's the precision BOSS achieved on a galactic scale. The wall itself is a marvel of cosmic engineering. Its galaxies aren't randomly scattered but aligned along dense filaments, intersecting at nodes where massive clusters collide. One such node, the Sloan Great Wall, appears to connect to it like a tributary feeding into a river. Yet here's what's truly groundbreaking. Simulations suggest structures this vast shouldn't form so late in cosmic history. The Great Wall defies expectations, hinting that dark energy, the mysterious force accelerating the universe's expansion, might play a more complex role in shaping large-scale structure than we thought. But the real story is how surveys like BOSS are rewriting the cosmic map. By combining redshift data with gravitational lensing and X-ray observations, astronomers now see the universe in 3 dimensions, revealing patterns invisible to traditional telescopes. The BOSS survey didn't just find a wall, it uncovered an entire network of filaments, proving that what we once called empty space is anything but. As next-generation telescopes like the Dark Energy Spectroscopic Instrument come online, they'll probe even deeper, potentially finding structures that make the Great Wall look small. Every new map reminds us the universe's grand design is far stranger and far more intricate than we ever imagined. And the most exciting part, we're only just beginning to trace its outlines. Before astronomers discovered the CFA2 Great Wall in 1989, the universe seemed like a relatively orderly place, galaxies clustered in groups, floating in what appeared to be mostly empty space. Then came this, a wrinkle in the cosmic fabric so immense it forced scientists to rethink everything. Stretching 500 million light-years across the northern sky, the CFA2 Great Wall wasn't just big, it was a revolution. Imagine mapping your neighborhood for years, thinking you knew every street and park, only to suddenly realize your entire town was just one block in a metropolis you never noticed. That's the scale of the paradigm shift this discovery triggered. What made the CFA2 wall so groundbreaking wasn't just its size, it was the way it revealed hidden patterns in the cosmos. Using redshift surveys from the Harvard-Smithsonian Center for Astrophysics, hence the CFA, in its name, astronomers Margaret Geller and John Huckrup painstakingly plotted galaxy positions, expecting a random distribution. Instead, they found galaxies lining up like beads on a string, forming a vast, flattened structure that dwarfed anything previously known. This wasn't a loose gathering of galaxies, it was a celestial freeway with lanes of matter stretching farther than anyone thought possible. Suddenly, the universe wasn't just sprinkled with galaxies, it was woven together in a tapestry of unimaginable scale. The discovery sent shockwaves through astronomy. Before the CFA2 wall, the prevailing assumption was that matter should distribute itself evenly across vast distances, a principle called homogeneity. But here was proof that even on scales of hundreds of millions of light-years, the universe preferred structure over randomness. It was as if gravity had been quietly playing a game of cosmic connect-the-dots, linking galaxies across distances so vast they defied intuition. The wall's sheer existence forced scientists to confront an uncomfortable truth. Their models of cosmic evolution were missing something fundamental about how matter clumps together over time. Yet for all its grandeur, the CFA2 Great Wall had secrets it wasn't ready to give up. Later surveys revealed it might be part of an even larger structure, a filament connected to other superclusters, hinting that what we thought was a standalone feature might just be one thread in an even grander design. And while newer discoveries like the Sloan Great Wall have since overshadowed its scale, the CFA2's legacy endures. It was the first crack in the cosmological principle, the first glimpse of a universe far more structured and far stranger than we ever imagined. What's remarkable is how this discovery reshaped the tools of astronomy itself. The painstaking redshift surveys that revealed the CFA2 wall paved the way for modern mega projects like the Sloan Digital Sky Survey, proving that sometimes the biggest breakthroughs come not from looking deeper but from looking wider. The universe, it turns out, had been hiding its grandest designs in plain sight all along. We just needed to step back far enough to see them. Here's something that might unsettle your cosmic bearings. Our Milky Way isn't just floating through space. It's sitting inside an unfathomable cosmic bubble called the KBC void, a spherical emptiness stretching 2 billion light-years across. That's right, we aren't in one of those dense, galaxy-packed superclusters. Instead, we're marooned in one of the largest voids ever discovered, a vast desert where galaxies are scattered so thinly that if you stood at its center, the night sky would appear shockingly dark. So how does being inside this void warp our view of the universe? It starts with cosmic speed. When astronomers measure how fast the universe is expanding, they rely on the brightness of distant supernovae and the motion of galaxies. But because we're nestled in this underdense region, the gravitational pull around us is weaker than in galaxy-rich areas. That means everything outside our void is moving away just a little faster than our models predict, like paddling upstream while the river's current tugs harder on objects downstream. The result, we might be underestimating the expansion rate of the universe, a discrepancy that's fueled heated debates about dark energy and the Hubble constant. But the KBC void's influence doesn't stop there. It also skews our perception of cosmic structure. From inside this emptiness, the rest of the universe appears more crowded than it really is, like peering out from a quiet valley onto distant mountain ranges and mistaking them for the norm. That distortion affects how we map galaxy distribution, potentially hiding even larger voids or exaggerating the density of superclusters beyond our bubble. It's as if we've been trying to study Earth's geography while standing in the middle of the Sahara. Our sample is biased by our lonely vantage point, yet there's an upside to our void-dwelling existence. The sparse surroundings mean fewer galactic collisions, giving the Milky Way a relatively peaceful neighborhood to evolve in. While galaxies in dense clusters get twisted and shredded by gravitational encounters, ours has had billions of years to form spiral arms, nurture stars, and crucially develop life without constant cosmic disruptions. Maybe the universe's largest voids aren't just wastelands, they're quiet incubators for complexity. The KBC void forces us to confront a humbling truth. We don't just observe the cosmos from a neutral point. Our address in space tints everything we see, measure, and theorize. Future telescopes like the Nancy Grace Roman Space Telescope aim to correct for this bias by mapping galaxy distributions on unprecedented scales. Until then, the void reminds us that sometimes, to understand the universe's grand design, we first need to step back and question our place within it. The universe holds one of its most unsettling secrets, not in what we can see, but in how things mysteriously move. Across vast distances, entire galaxy clusters are streaming in the same direction at astonishing speeds, over 2 million miles per hour toward something we can't see, something beyond the very edge of our observable universe. Astronomers call this the dark flow, and it's as if the cosmos itself is whispering about forces we haven't yet imagined. This bizarre motion was first detected in 2008, when scientists studying the cosmic microwave background noticed something odd. The remnant glow from the Big Bang showed subtle temperature shifts, revealing that hundreds of galaxy clusters were being pulled toward a single point in space, far outside the boundaries of what we can observe. It's like watching leaves caught in a river current, all drifting the same way, except here, the current spans billions of light years and its source is completely invisible. So what could possibly tug on entire clusters from beyond our cosmic horizon? One radical theory suggests the gravitational influence of another universe, a neighboring bubble in the multiverse pressing against our own. If true, this would mean the dark flow isn't just a curiosity. It's the first observable evidence of realities beyond our own, their gravity leaking through the fabric of space-time. Other explanations propose massive concentrations of dark energy, or even exotic defects in the structure of the early universe left over from cosmic inflation, ancient wrinkles in reality tugging matter toward them like cosmic magnets. Skeptics argue it could be a statistical fluke or a misreading of the data, but follow-up studies have only deepened the mystery. The dark flow persists, aligning with no known supercluster or void, defying the expected distribution of matter in our universe. It challenges one of cosmology's core assumptions, that the universe should be roughly uniform on the largest scales. Instead, the dark flow hints at an asymmetry, a great beyond pulling strings we can't yet comprehend. Future missions like the Euclid Space Telescope aim to map this motion with unprecedented precision, potentially revealing whether the flow strengthens, weakens, or changes direction at even greater distances. Whatever the answer, the dark flow reminds us that the universe still guards its grandest mysteries just out of sight, and that sometimes the most profound discoveries begin not with what we see, but with what inexplicably moves. At a certain scale, about 300 million light-years, something strange happens to the fabric of the universe. The intricate web of galaxy clusters, superclusters, and filaments that dominate smaller distances suddenly dissolves into a smoother, almost featureless expanse. Cosmologists call this transition the end of greatness, the point where the universe stops looking like a carefully constructed cosmic web and instead appears nearly uniform, no matter where you look. It's as if you've zoomed out on a pointillist, painting the individual dots that once formed vivid shapes blur into a wash of color, losing their structure as distance erases their distinctions. Why does this transition matter? Because it tests one of cosmology's foundational ideas, the cosmological principle. This principle states that on sufficiently large scales, the universe should look roughly the same everywhere with no special locations or preferred directions. For decades, this was just an elegant assumption until astronomers actually measured it. By painstakingly mapping galaxy distributions across vast distances, they found that while the cosmos is undeniably clumpy up close, those wrinkles smooth out beyond the 300 million light-year threshold. It's not just a curiosity, it's a cosmic Rubicon, marking the boundary where gravity's local tug-of-war gives way to the broader, smoother influence of dark energy and the universe's expansion. But here's the twist: not everyone agrees on where exactly this transition happens. Some studies suggest the end of greatness might occur even earlier, around 250 million light-years, while others argue the true scale could be larger. The debate hinges on how we define structure. Are we talking about galaxy clusters, filaments, the voids between them? Each leaves its own fingerprint on the universe's large-scale distribution, and depending on what you measure, the answer shifts. What's undeniable is that this transition exists, and it tells us something profound about how gravity and dark energy have shaped the cosmos over billions of years. The end of greatness isn't just a philosophical boundary, it has real implications for how we study the universe. For instance, when astronomers measure the universe's expansion rate, they rely on the assumption that, beyond a certain scale, matter is evenly distributed. If that assumption breaks down, if structures persist larger than expected, it could throw off our calculations of dark energy's influence or even the universe's ultimate fate. Similarly, simulations of cosmic evolution must account for this transition to accurately model how galaxies form and cluster. What's fascinating is that this limit isn't arbitrary. It reflects the universe's age and the speed at which gravity can assemble matter. In a younger cosmos, there wouldn't have been enough time for structures to grow this large. In an older one, perhaps even vaster formations might emerge. The end of greatness, then, is like a cosmic clock, ticking off the epochs of structure formation and revealing just how far gravity's reach extends before dark energy takes over. As telescopes peer deeper into space, probing ever larger scales, we might yet find surprises that push or redefine this boundary. Maybe the universe isn't as uniform as we thought, or perhaps there are even grander structures lurking beyond our current observational limits. For now, the end of greatness stands as a reminder that even in the vastness of space, there are rules, and the cosmos is still teaching us how to read them. Stretching across the cosmos like a colossal bridge, some of the universe's largest structures, including the Sloan Great Wall and the Hercules-Corona Borealis Great Wall, appear to align with something even more fundamental: the cosmic microwave background itself. Astronomers call this eerie coordination the axis of evil, and it's not just a quirky name, it's a direct challenge to one of cosmology's most cherished principles. According to the Standard Model, the universe should have no preferred direction. Matter and radiation ought to distribute randomly, like sprinkles scattered across a cupcake. But when scientists mapped the CMB's temperature fluctuations against the orientation of these vast galactic walls, they found an unsettling pattern. These structures seem to line up with the CMB's coldest and warmest spots, as if the universe had quietly drawn a giant arrow pointing towards something beyond our current understanding. So why does this alignment rattle physicists? Because it hints that either our observations are biased in some bizarre way, or more thrillingly, the early universe wasn't as uniform as we thought. One theory suggests that cosmic inflation, the rapid expansion of space just after the Big Bang, might have left behind imprints in spacetime itself, like wrinkles in a stretched sheet, nudging matter into unexpected large-scale patterns. Others propose even wilder ideas. Perhaps the axis of evil marks the gravitational tug of a neighboring universe beyond our observable horizon, or evidence of exotic physics before the Big Bang. It's as if we've been studying a painting, only to realize the brushstrokes align with a frame we never noticed. the implications ripple far beyond mere curiosity. If the axis of evil is real, it could mean our universe has a preferred direction, undermining the cosmological principle that has guided astronomy for decades. Dark energy might behave differently along this axis, or gravity itself could have subtle variations we've yet to detect. Even the Hubble constant, the rate of the universe's expansion, might need recalibrating if space stretches unevenly. Skeptics argue it could be a statistical fluke, but the persistence of this alignment across multiple datasets keeps the debate alive. What's next? Future CMB experiments like the Simons Observatory aim to measure polarization patterns with unprecedented precision, potentially revealing whether the axis of evil is a cosmic coincidence or a fracture in our understanding of reality. Until then, this mysterious alignment stands as a humbling reminder. The universe might still be keeping its biggest secrets, not in the darkness between galaxies, but in the subtle patterns we're only beginning to trace. The Eridanus supervoid isn't just another empty patch of space. It's a yawning cosmic chasm so vast it could swallow thousands of Milky Ways without a trace. Stretching 1.8 billion light-years across the constellation Eridanus, this staggering underdense region contains only about 20% of the galaxies you'd expect in a space that size. But what makes it truly remarkable isn't just its emptiness, it's the eerie way this void lines up with one of cosmology's greatest mysteries, the cold spot in the cosmic microwave background radiation. When astronomers first mapped the CMB, the afterglow of the Big Bang, they expected a near-uniform distribution of temperature variations. Instead, they found an unusually cold patch right where the Eridanus supervoid sits. At first glance, this seems logical. If light travels through a void, it should lose energy climbing out of the weaker gravitational field, creating a cooler spot in the CMB, a process called the integrated Sachs-Wolf effect. Think of it like rolling a ball up a shallow hill. The less steep the incline, the more energy the ball loses. But here's where the math falls apart. The Eridanus supervoid, while enormous, isn't empty enough to account for the cold spot's extreme temperature dip. To create that level of cooling, you'd need a void at least 3 times denser, or some other exotic physics at play. This discrepancy has sparked fierce debate among cosmologists. One camp argues we're seeing a statistical fluke, the cosmic equivalent of flipping a coin and getting tails 20 times in a row, random but not impossible. Others propose more radical explanations. Could the void be filled with an unknown form of dark energy, accelerating its expansion from within? Might it be the imprint of a collision between quantum bubbles in the early universe? Or perhaps most mind-bending of all, could it be evidence of another universe's gravity leaking into ours through higher dimensions? The intrigue deepens when you consider how voids form. The leading theory suggests they're cosmic drainage basins, regions where matter was siphoned away by surrounding superclusters over billions of years. Yet the Eridanus supervoid's near-perfect spherical shape defies this explanation. Natural voids tend to be irregular, like holes in Swiss cheese, not flawless bubbles. Some researchers speculate it might be a supervoid, not just one void but a nesting doll of smaller empties layered together, amplifying its effect. Others wonder if it's a relic of primordial sound waves from the Big Bang itself, frozen in the fabric of space-time. What's at stake here goes far beyond one curious cold patch. If the Eridanus supervoid and the CMB anomaly are truly connected, it could mean our understanding of dark energy, gravity, or even the multiverse is fundamentally incomplete. Future telescopes like the Vera Rubin Observatory plan to map millions more galaxies, probing the void's structure with unprecedented precision. Until then, this billion-light-year enigma remains a humbling reminder. Sometimes, the most profound cosmic mysteries aren't found in the glittering galaxies, but in the vast, whispering emptiness between them. While we often picture the Milky Way drifting through a sea of galaxies, The truth is far lonelier. Our galactic neighborhood sits on the edge of a staggering emptiness called the local void, a dark expanse spanning 150 million light-years with hardly any galaxies at all. Imagine standing in a sprawling desert where the nearest town is so distant you'd need to walk for lifetimes just to reach it. That's the scale of isolation we're talking about. Yet this void isn't just empty space, it's an active player in the cosmic dance, shaping how galaxies like ours move and evolve. For decades, astronomers assumed the space around us was relatively average, until detailed mapping revealed we're actually perched on the edge of this immense nothingness. The local void isn't a perfect sphere but a complex, irregular bubble, its boundaries traced by the handful of reluctant galaxies clinging to its edges, including our own Milky Way. Here's the twist: voids aren't static. They expand over time as gravity pulls matter toward denser regions like superclusters, leaving behind ever-growing deserts. This means the local void is actively pushing our galaxy away, contributing to the Milky Way's motion alongside the pull of the Great Attractor and the Shapley supercluster. It's like being in a tug of war where one team is an invisible ghost. You can't see the force, but you feel its effects. Studying voids like this one isn't just about cataloging empty space, it's a window into the universe's skeleton. Voids make up the majority of cosmic volume, their boundaries outlining the filaments and walls of the cosmic web. By mapping their shapes and sizes, astronomers can reconstruct how dark matter and dark energy have sculpted the universe over billions of years. The local void, for instance, has taught us that galaxies near voids often show unusual properties: slower star formation, older stellar populations, as if the emptiness itself puts them into cosmic hibernation. What's truly fascinating is how voids challenge our perception of scale. The local void might seem vast, but it's dwarfed by giants like the Boötes void, proving that even nothingness comes in different sizes. Yet every void, no matter how empty, holds clues. The faint ripples in the cosmic microwave background, the peculiar motions of nearby galaxies, even the distribution of distant quasars, all bear the imprint of these cosmic bubbles. As telescopes like the Vera Rubin Observatory begin mapping millions more galaxies, they'll reveal voids we never knew existed, painting a clearer picture of the universe's true structure. And while the local void might seem like a mere blank spot on the map, it's a reminder that sometimes the most profound cosmic stories aren't written in the glitter of stars, but in the silent spaces between them. What if I told you the universe's grandest structures aren't made of stars or galaxies at all? They're woven from something invisible: dark matter, the universe's hidden architect. While we marvel at galaxy clusters and cosmic walls, these visible formations are merely ornaments hanging from an even vaster scaffolding, a gravitational skeleton stretching across the cosmos. This is the dark matter cosmic web, and it's the real blueprint behind everything we see. Picture a spiderweb glistening with dew. The droplets are like galaxies clinging to nearly invisible strands. That's how dark matter works. It doesn't emit or reflect light, yet its gravitational pull is so dominant that it dictates where galaxies form and how they move. Without this unseen framework, the universe would be a shapeless void, its matter too thinly spread to ever coalesce into the glittering structures we observe. The cosmic web we see, the Sloan Great Wall, the Hercules-Corona Borealis Great Wall, are just the brightest threads in a tapestry mostly stitched from darkness. So how do we map something we can't see? Astronomers have devised ingenious methods to trace this invisible architecture. One technique relies on gravitational lensing, the way dark matter bends light from distant galaxies, distorting their shapes like a funhouse mirror. By analyzing these distortions, scientists can reconstruct the hidden mass warping spacetime. Another approach tracks galaxy movements. Just as leaves floating on a river reveal unseen currents, galaxies' motions betray the pull of dark matter filaments connecting them. The most ambitious projects, like the Dark Energy Survey, combine millions of these observations to build 3D maps of the cosmic web's dark foundations. Here's where it gets even wilder. Recent simulations suggest dark matter filaments aren't just passive backdrops, they're cosmic highways, channeling gas into galaxy clusters and feeding supermassive black holes. Some theories propose these filaments might even harbor dark galaxies, clumps of dark matter so dense they could host stars without any visible matter at all. And though we still don't know what dark matter actually is, its fingerprints are everywhere, from the spin of galaxies to the clustering of the entire observable universe. The most astonishing part, this web might be even larger than we think. Some models hint that dark matter structures extend beyond our observable horizon, meaning the true scale of the cosmic web could dwarf even the Hercules-Corona Borealis Great Wall. As new telescopes like the Vera Rubin Observatory come online, they'll peel back more layers of this invisible framework, revealing how darkness sculpted the light-filled universe we call home. We're living in a cosmic house built by unseen hands, and every new map of the dark matter web brings us closer to understanding the master builder behind it all. The universe's greatest structure isn't just hiding in plain sight, it's the very reason anything is visible at all. Imagine if the universe's largest structures weren't just sculpted by gravity, they were literally written in sound. That's the story of Baryon acoustic oscillations, frozen ripples from the Big Bang that still echo through the cosmos today. Picture the early universe as an unimaginably dense hot plasma, a soup of particles so tightly packed that light couldn't travel freely. In this primordial fireball, gravity pulled matter inward while radiation pressure pushed outward, creating cosmic sound waves that reverberated for hundreds of thousands of years. When the universe finally cooled enough for atoms to form, these waves froze in place, leaving behind a subtle pattern in the distribution of matter, a cosmic fingerprint we can still detect 14 billion years later. What makes these oscillations so remarkable is their precision. Unlike random clumps formed by gravity alone, Baryon acoustic oscillations created a preferred spacing between galaxies, like an invisible ruler stamped across the cosmos. Scientists measure this scale at about 500 million light-years, meaning galaxy clusters tend to be separated by this distance more often than chance would predict. It's as if the universe itself was tuned to a specific frequency, and that melody still shapes cosmic structure today. Detecting these ancient ripples required mapping millions of galaxies in 3 dimensions, a task only possible with modern redshift surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument. When astronomers plotted galaxy positions, they noticed an odd pattern. Galaxies were slightly more likely to be found at a certain distance from each other, creating what looks like a vast 3-dimensional shell structure. This isn't just statistical noise, it's the fossilized imprint of those primordial sound waves, preserved across billions of years of cosmic evolution. But why does this matter beyond cosmic archaeology? Because these oscillations serve as a standard ruler for measuring the universe's expansion. By comparing the observed scale of these patterns with their known original size from the early universe, scientists can track how space has stretched over time. This has become one of our most powerful tools for studying dark energy, the mysterious force accelerating the universe's expansion. The oscillations also help us weigh the cosmos literally. Their spacing depends on the total amount of matter in the universe, both visible and dark, giving us an independent way to measure what's out there. What's truly astonishing is how something so subtle, a mere 10% enhancement in galaxy clustering at specific scales, could reveal so much about the universe's history and fate. Those frozen sound waves connect us directly to the universe's infancy, linking the first microseconds after the Big Bang to the grand cosmic web we see today. And as next-generation telescopes map ever more distant galaxies, we'll read this cosmic sheet music in ever greater detail, uncovering new verses in the universe's oldest song. Before galaxies, before stars, even before the first flickers of light pierced the cosmic darkness, the universe was quietly knitting together its first large-scale structures, not as majestic spirals or blazing clusters, but as something far stranger, vast, flattened sheets of matter cosmologists call Zeldovich pancakes. The name might sound whimsical, but the physics behind them is anything but. Picture the early universe not as a smooth soup of particles, but as a turbulent sea of tiny density fluctuations, microscopic ripples left over from the Big Bang itself. Gravity acted like an invisible hand, pulling matter toward these slightly denser regions over hundreds of millions of years. But with a twist, instead of forming spherical clumps, the first structures collapsed along one axis first, like a pancake being pressed flat on a griddle. What makes these pancakes so revolutionary is how they solve a cosmic chicken and egg problem. Traditional models suggested galaxies formed first, then clustered together into larger structures. But Soviet physicist Yakov Zeldovich flipped that script in the 1970s, arguing that immense sheets of gas and dark matter stretching millions of light-years across condensed first, only later fragmenting into the galaxies we recognize today. Imagine building a city by first laying out entire boroughs as blank concrete slabs, then carving individual streets and buildings. That's the scale of reorganization Zeldovich proposed. These primordial pancakes weren't just theoretical curiosities. They left fingerprints we can still detect. As matter collapsed into these flattened sheets, shock waves rippled through them, heating gas to extreme temperatures and seeding the conditions for future star formation. Some astronomers believe the oldest, most metal-poor stars in our galaxy might be refugees from these pancake fragments, ancient survivors of a time when the universe's structure was still being forged. Even more intriguing, simulations suggest these sheets didn't just vanish, their ghosts might linger in the cosmic web, with today's galaxy filaments tracing the outlines of those first collapsed regions. Yet here's where the story takes a turn. While Zeldovich's predictions brilliantly explained the universe's filamentary structure, they also revealed a paradox. If pancakes formed so early, why don't we see more remnants of them? One answer lies in dark matter's behavior. Unlike ordinary matter, dark matter doesn't collide or generate shock waves. It streams smoothly through space, meaning those early sheets might have formed and dissolved without leaving obvious visible traces. It's like trying to reconstruct a snowfall from the puddles it left behind. The evidence is there, but you need to know where to look. Modern telescopes are finally giving us glimpses of this pancake era. Observing the distant universe with instruments like the James Webb Space Telescope is like rewinding time, letting us spot regions where gas is just beginning to condense into these proto-structures. Meanwhile, dark matter maps from projects like the Euclid space mission might reveal the gravitational scaffolding that guided their formation. The more we learn, the clearer it becomes. Our universe didn't assemble itself piece by piece. It folded, flattened, and fractured into existence, with Zeldovich's pancakes as the first delicate creases in the cosmic origami. What's astonishing is how this 70-year-old theory still shapes our understanding of cosmic evolution. Those hypothetical pancakes weren't just a stepping stone. They were the blueprint for everything that followed, from the tiniest dwarf galaxies to the largest superclusters. And as we peer deeper into the universe's infancy, we're not just uncovering how structures formed, we're witnessing the moment gravity itself learned to cook. Right now, the universe's greatest walls, structures like the Hercules-Corona Borealis Great Wall and the Sloan Great Wall, are held together by gravity, their galaxies bound in a delicate dance across billions of light years. But the cosmos isn't static. Dark energy, the mysterious force accelerating the universe's expansion, is slowly stretching space itself, and over time, its influence could reshape these colossal formations in ways that defy imagination. Picture a slow-motion tug-of-war where one side keeps getting stronger. Gravity may be holding these walls together today, but dark energy is the relentless opponent that never stops pulling. The fate of these structures hinges on a simple but profound question. Can gravity's grip outlast dark energy's push? Current models suggest that within tens of billions of years, galaxies at the edges of these walls will begin drifting apart faster than gravity can pull them back. It's like trying to keep a sandcastle intact as the tide rises eventually. Even the strongest bonds will dissolve. The first to go will be the most distant galaxies in these superclusters, their light shifting to infrared, then fading entirely as expansion carries them beyond our observable horizon. Over even longer timescales, the walls themselves will thin, their majestic filaments fraying as the space between galaxies grows too vast for gravity to bridge. But here's the twist: not all walls will meet the same fate. Denser regions where galaxies cluster more tightly might hold on longer, even as the voids between them stretch into near infinite emptiness. The densest nodes, places like the Shapley supercluster, could persist as isolated islands in an ever-expanding sea of darkness, their surviving galaxies orbiting one another in tight, doomed circles. Meanwhile, the outer filaments of these walls will stretch and snap, their galaxies scattering like beads from a broken necklace, each destined to drift alone through an increasingly empty cosmos. What's truly unsettling is the timescale. While stars in our galaxy will burn out in mere tens of billions of years, the Great Walls could linger in some form for hundreds of billions, ghosts of structures that once defined the universe's architecture. Eventually, though, even the most massive clusters will succumb. With expansion accelerating exponentially, dark energy will win the war, tearing apart galaxy groups, then individual galaxies, and finally even stars themselves. It's a future where the universe's largest structures aren't just dissolved, they're erased from existence entirely. Their light stretched beyond detectability, their matter scattered beyond recovery. Yet this grim fate isn't set in stone. Some theories suggest dark energy might evolve, weakening or even reversing its push over time. Others propose that unknown physics, new forces or dimensions could rewrite this outcome entirely. For now, though, the Great Walls stand as monuments to a fleeting era of cosmic structure, reminders that even the mightiest things in the universe are temporary. Their future may be one of dissolution, but their present tells a story of gravity's triumph, a fleeting moment in cosmic history when matter wove itself into patterns grand enough to span the sky. At the heart of nearly every massive galaxy, and certainly at the crossroads of every cosmic wall and filament, lurks a gravitational monster so powerful it shapes the destiny of matter for millions of light years around it, a supermassive black hole. These aren't just passive sinkholes in space, they're dynamic engines actively sculpting the universe's largest structures by anchoring entire galaxy clusters at the intersections of the cosmic web. Picture a spider sitting at the center of its web, not just resting there, but tightening certain strands and vibrating others to control the entire network. That's the role supermassive black holes play in the grand architecture of the cosmos. Take the Phoenix cluster, for example. 3.8 billion light-years away, this galaxy cluster hosts one of the most active black holes ever observed, pumping out energy that heats surrounding gas to millions of degrees. Far from disrupting the cluster, this ferocious output actually regulates star formation across hundreds of galaxies, preventing gas from cooling too quickly and collapsing into new stars. It's a cosmic feedback loop on an unimaginable scale. The black hole's outbursts create vast bubbles in the intergalactic medium, which rise like balloons, redistributing heat and matter across the cluster. Without this violent balancing act, galaxies in dense clusters would burn through their fuel too fast, leaving the universe's most massive structures devoid of new stellar generations. But how do these gravitational behemoths end up at structure intersections in the first place? The answer lies in the cosmic web's growth. As dark matter filaments funnel gas toward their intersections over billions of years, galaxies collide and merge, their central black holes eventually sinking to the new galactic core through a process called dynamical friction. The largest mergers create black holes weighing tens of billions of suns like Ton 618, a quasar whose black hole weighs 66 billion solar masses. Such monsters don't just sit quietly, their gravitational influence extends far beyond their host galaxies, warping the paths of nearby galaxy clusters and even altering how filaments of the cosmic web connect around them. What's truly astonishing is how these black holes imprint their presence on scales we're only beginning to map. The Event Horizon Telescope's image of M87's black hole revealed not just the shadow of the singularity itself, but also the vast jets of plasma stretching thousands of light-years, visual proof of how black holes channel energy along the cosmic web's filaments. Similarly, the E-Rosetta X-ray telescope has mapped bubbles of hot gas around active black holes that span the distance between galaxies, showing how these engines redistribute matter across entire superclusters. Yet the most profound revelation might be how black holes and large-scale structure co-evolve. The same filaments that feed galaxies also funnel gas toward their central black holes, triggering outbursts that then heat the surrounding web, creating a self-regulating cosmic ecosystem. In this dance, black holes aren't just passengers, they're architects, shaping the very infrastructure that sustains them. As we peer deeper into the universe's scaffolding, we're finding that these invisible giants don't merely inhabit the cosmic web, they helped weave it. We think of the universe's matter as neatly accounted for: stars, galaxies, planets, all visible, measurable. But here's the cosmic shocker: roughly half the normal matter, the protons and neutrons that make up everything we can see, was missing for decades. This is the missing Baryon problem, one of astronomy's most stubborn puzzles. Where could an entire universe's worth of atoms vanish? The answer lies not in some exotic dimension, but in the faintest, most pervasive structures of all, the ultra-thin tendrils of gas strung between galaxies like gossamer threads in a spiderweb. For years, simulations predicted that these filaments of the cosmic web should contain most of the universe's baryonic matter, ordinary atoms, not dark matter or dark energy. But spotting them proved nearly impossible. Unlike blazing stars or glowing nebulae, this gas is so diffuse and cool it emits almost no light. Imagine trying to photograph a whisper-thin mist at twilight. It's there, but almost invisible to conventional telescopes. The breakthrough came when astronomers realized they didn't need to see the gas directly. Instead, they could hunt for its shadow. Here's how it works. When light from distant quasars passes through these filaments, certain wavelengths get absorbed by the gas, leaving faint fingerprints in the quasar's spectrum. It's like holding a prism up to a spotlight and seeing dark bands where specific colors have been siphoned away. The telltale signatures of oxygen and hydrogen ions finally betrayed the hidden baryons, revealing a reservoir of matter so vast it could solve the missing mass problem at a stroke. But there's a twist. This gas isn't just floating idly in space. It's scorching hot, heated to millions of degrees by the gravity of collapsing filaments and the energy of nearby galaxies. At these temperatures, the gas emits X-rays, but so faintly that only the most sensitive detectors, like the European Space Agency's XMM Newton telescope, could catch glimpses. Even now, mapping this cosmic fog requires stitching together thousands of observations, painstakingly separating the signal from the noise. What's incredible is how these filaments fit into the larger cosmic puzzle. They aren't just storage units for missing matter, they're the universe's plumbing system, channeling gas into galaxies and fueling new star formation. Without them, galaxies would starve, their growth stunted by a lack of raw material. Yet for all their importance, these filaments are delicate. The gravitational tug of dark matter may have drawn them into existence, but dark energy's relentless push could one day tear them apart, scattering their atoms beyond recovery. The discovery of these baryon-rich filaments doesn't just fill a gap in our accounting, it reshapes how we see the cosmic web. What we once thought of as empty space is actually a dynamic network of rivers and reservoirs quietly sustaining the universe's grand structures. And as new telescopes like Athena come online, probing even deeper into this hidden infrastructure, we may find that the missing matter was never lost at all, just waiting for us to develop the tools to see it. When we compare the universe's largest observed structures, like the Hercules-Corona Borealis Great Wall or the giant Arc, to supercomputer simulations of cosmic evolution, something peculiar happens. The simulations, based on our best understanding of dark matter, dark energy, and gravity, consistently produce structures that are impressive, but not quite as jaw-droppingly vast as what we actually see out there. It's like building a model of a city based on zoning laws, only to discover the real thing has skyscrapers twice as tall as the rules should allow. This discrepancy isn't just academic, it could mean our cosmic rulebook is missing a few critical chapters. Take the Hercules-Corona Borealis Great Wall. Spanning 10 billion light-years, it defies what's known as the homogeneity scale, the distance beyond which the universe should appear roughly uniform. Current simulations, running on meticulously tuned parameters of the standard cosmological model, dubbed lambda CDM, rarely produce single structures stretching beyond 1.2 billion light-years. Yet here we are, staring at formations nearly 10 times that size. Some researchers argue this might point to flaws in how we simulate initial conditions, those tiny quantum fluctuations from the Big Bang that seeded all cosmic structure. Perhaps those early ripples weren't as random as we thought, containing hidden patterns that snowballed into unexpectedly colossal formations. Then there's the matter of timing. The universe is only 13.8 billion years old, barely enough time, according to conventional physics, for gravity to assemble matter into the titanic walls and filaments we observe. Simulations often rely on dark matter's gravitational pull as the primary architect, but what if dark energy, the mysterious force accelerating cosmic expansion, played a more complex role in the early universe? Some cutting-edge models suggest dark energy might have fluctuated in strength, alternately boosting and suppressing structure growth in ways we haven't accounted for. It's like realizing the blueprint for a building omitted the effects of wind. Once you include it, the whole design shifts, the most provocative possibility. That we're seeing fingerprints of physics beyond our current models. Certain modified gravity theories, like modified Newtonian dynamics, attempt to explain cosmic structure without dark matter, but they struggle to reproduce the web-like patterns we observe. More radical ideas propose that early universe phenomena, cosmic strings, domain walls, or even collisions between bubble universes left behind imprints that guided matter into these improbable megastructures. Others speculate that dark matter isn't the simple, sluggish particle we've assumed, but a more dynamic substance with properties that amplify clustering on vast scales. Yet before we rewrite the textbooks, there's another explanation worth considering: that our observations are being misinterpreted. The fingers of God effect, for instance, can make galaxy clusters appear elongated along our line of sight due to their internal motions, potentially exaggerating structure sizes. Similarly, what looks like a single coherent wall might instead be smaller structures aligned by chance, like scattered clouds forming what seems to be a face when viewed from just the right angle. Future surveys like the Euclid Space Telescope aim to settle these debates by mapping billions of galaxies in 3D, separating true cosmic architecture from illusions of perspective. What makes these simulations so valuable despite their current limitations is their predictive power. They serve as cosmic laboratories, letting us test how tweaks to initial conditions or physical laws ripple through virtual universes. When simulations consistently fall short of reality, it's not a failure, it's a clue. The universe's largest structures might be more than just curiosities. They could be signposts pointing toward deeper truths about dark matter's nature, gravity's behavior at extreme scales, or even the possibility that our observable universe is just one patch in a far grander, inhomogeneous cosmos. The conversation between observation and simulation is far from over. Each new discovery of a massive structure adds another piece to the puzzle, while supercomputers grow powerful enough to simulate larger volumes of universe with finer detail. Whether the resolution comes from refined models, exotic physics, or better observations, one thing is certain: the universe's grandest designs still have secrets to reveal, and our simulations are the flashlight helping us trace their outlines in the dark. All this time, we've been marveling at structures spanning billions of light years, but here's the cosmic twist: they shouldn't be possible. According to our best models, there's a fundamental limit to how big cosmic structures can grow. It's called the homogeneity scale, and it caps things at around 1.2 billion light years. Beyond that, the universe should smooth out, with matter distributed evenly in all directions. Yet we keep finding walls, voids, and filaments that bulldoze right through this theoretical boundary, stretching 2, 5, even 10 billion light years across. So what gives? Either our understanding of cosmic evolution is missing something profound, or we're staring at the edge of reality itself. The root of this limit traces back to the Big Bang. In the universe's first fractions of a second, space expanded exponentially during a period called inflation, stretching quantum fluctuations into slight density variations. These tiny ripples became the seeds for all structure-denser regions, attracted more matter via gravity, eventually forming galaxies and clusters. But here's the catch: the speed of light and the age of the universe impose a ceiling. In 13.8 billion years, gravity simply hasn't had enough time to organize matter into single coherent structures larger than 1.2 billion light years. It's like trying to build a sandcastle taller than your shovel can reach. The physics just doesn't allow it. Yet the Hercules-Corona Borealis Great Wall laughs at this constraint. At 10 billion light years, it's not just nudging past the limit, it's vaulting over it with room to spare. One explanation: these megastructures might not be single unified objects, but chance alignments of smaller formations, like clouds that happen to form the shape of a dragon when viewed from Earth. But even if that's true, the statistical odds of such alignments are vanishingly small. Another possibility is that dark energy, the force accelerating cosmic expansion, behaved differently in the past, briefly supercharging gravity's ability to knit matter together before switching roles and pushing everything apart. Then there's the elephant in the room. The observable universe itself is only 93 billion light years across. When structures like the giant arc span a significant fraction of that, we're forced to ask, are we seeing a true physical boundary, or just the edge of what we can observe? Beyond our cosmic horizon, space stretches infinitely, potentially hosting structures so vast they make our great walls look like specks. Some theories even suggest our entire observable universe could be a single bubble in a multiverse foam, with other bubbles harboring entirely different physical laws. If true, the anomalies we're spotting might be seams where our bubble brushes against others. The real enigma isn't just what lies beyond our horizon, it's whether the horizon itself is warping our perception. Light has a speed limit, so the farther we look, the further back in time we see. The Hercules-Corona Borealis Great Wall, for instance, appears as it was when the universe was barely 4 billion years old. Could its apparent size be a mirage stretched by the universe's expansion? Or does it hint that the early cosmos had wilder, more extreme density variations than our models predict? Upcoming telescopes like the Nancy Grace Roman Space Telescope aim to probe these questions by mapping galaxy distributions in unprecedented detail, searching for patterns that might reveal whether these giants are cosmic rule breakers or signs that the rules themselves need rewriting. So where does this leave us? On the knife edge of discovery, staring at structures that defy explanation. maybe the answer lies in undiscovered physics, a fifth fundamental force, or dark matter with unexpected properties. Or perhaps we're glimpsing something even stranger, evidence that our universe isn't the uniform expanse we thought, but a patchwork of regions with wildly different properties. One thing's certain, the universe's largest structures aren't just curiosities. They're stress tests for our deepest theories, bending the framework of cosmology until it creaks. And every time we think we've hit the ceiling, the cosmos tears it down and builds something bigger. The observable universe might have limits, but our understanding of it clearly doesn't. Whatever lies beyond that 93 billion light-year horizon, one truth remains: the universe has always been richer, weirder, and more defiantly complex than we ever imagined. And the greatest structures we've found so far, they might just be the opening act. From colossal walls of galaxies spanning billions of light years to unfathomable voids where darkness reigns supreme, the universe's largest structures defy everything we thought possible about scale and structure. These cosmic titans aren't just astronomical curiosities, they're the universe's way of showing us the limits of our understanding. Each discovery peels back another layer of the cosmic onion, revealing how gravity, dark matter, and dark energy have woven the fabric of reality over billions of years. The Hercules-Corona Borealis Great Wall alone, stretching 10 billion light-years, challenges our most fundamental assumptions, forcing us to question whether the universe truly follows the rules we've written for it. What makes these structures so invaluable isn't just their staggering size, but the secrets they hold about the universe's past and future. The cosmic web's filaments trace the gravitational blueprint of the early universe, preserving patterns from the Big Bang itself. Voids like Boötes show us how emptiness shapes galactic evolution, while anomalies like the cold spot hint at physics we can't yet explain. Every massive wall and desolate void acts as a cosmic laboratory, testing our theories about dark energy's acceleration, the nature of dark matter, and even the possibility of parallel universes. These aren't just static monuments, they're dynamic, evolving puzzles that rewrite the story of cosmic evolution with every new observation. Yet for all we've uncovered, the most tantalizing question remains: what lies beyond our observational horizon? If structures like the giant arc can span 3.3 billion light-years in the observable universe, what unimaginable formations might exist in the regions we can't see? Are these walls just the local branches of something even grander, a superstructure spanning tens of billions of light-years? Or does the cosmic web extend infinitely, with patterns repeating at scales so vast they dwarf human comprehension? So here's where we leave you staring up at the night sky with fresh eyes. The next time you look at the stars, remember they're not just scattered dots, but threads in a tapestry more intricate and expansive than we ever dreamed. What do you think lies beyond the edge of our observable universe? Even bigger walls, more mysterious voids, or something so strange we haven't even thought to name it yet? Drop your wildest theories in the comments, because when it comes to the cosmos, the only limit is our imagination.